This very brief coffee break. So we have two more speakers for the morning. So the first speaker is Tobias Kuna from Reading. He's gonna talk about he's gonna talk about typical behavior of extremes of chaotic dynamical systems or general observables. The floor is yours. I give you the 5 minutes time.
Thanks. Yeah. So I mean, as probably also the first one who's speaking somehow a bit more about the theory of extremes, I will give also a mini introduction into the theory, and somehow the main aim of the talk is our quest to find some. Oh yes. Otherwise, the world will lose all my voice then. Okay, so this is okay. It must be a bit higher. So, yeah. So what we try to discover is some connection between the characteristics of extremes and the underlying dynamical system, and to try to find this in some, let's say, regular way. So just to understand, to get some qualitative understanding of what is happening there. So, so what I will do is, the first thing I will introduce a general theory of extremes in the stochastic sense. Then I will give a mini introduction to extremes for dynamical systems, and I try to be as I try to explain this in a very general term, because somehow we have a very mixed audience. And then finally, I will discuss two types of observables and what will be somehow their different kind of properties. And I will apply linear response theory to the theory of extremes. And finally, I will state a long list of open problems. Okay. So let me start to explain what is the idea of an extreme value. So extreme value in this sense. I mean, in this sense, it means somehow the easiest, let's say, the paradigmatic example. I mean, this is clearly not an example of great interest, but this is somehow the paradigmatic one. So if you have a sequence of random variables and they are all independent, then somehow you look at the extremes under the first n, and so you make some kind of running extreme. You always somehow only count if you get bigger than you have ever been before. And the right thing to think about it is somehow that this is the same thing. It's a strong analogy with the sum, because they're both somehow associative. And essentially the theory, what I want to try to explain, the theory for the two is essentially the same. Now, the question is, when somehow we say a random variable fulfills an extreme value law, it fulfills an extreme value law if one can find two normalization constants such that an expression like this converges in distribution. Okay. So, and one can see from general theory, it follows that essentially the choice of A and B are essentially unique up to some kind of scaling, because I mean, I have here some, if you think about it, I have this kind of scaling symmetry, because there's somehow this kind of linear transformation. If I change it somehow, everything will transform along. And then I can show, and that's somehow the analog with respect to the central limit theorem. One can actually classify the limit laws. And one has essentially only three choices. So one can have somehow the one which is somehow tails off to infinity, and one which has somehow a threshold and which somehow goes up to the threshold, and then somehow the case which is somehow in between the two, which has somehow not a exponential polynomial, but an exponential kind of thing. And and the interesting thing is somehow this is somehow of practical importance, because this is actually a very stable result. So one can see somehow for the independent case, one can very nice and easily characterize the domain of attraction. I mean, if you start, so the question is, if you start with some distribution for your initial random variable x, where you will end up and when you will end up, and you can somehow, this can be exactly classified. So this very old theory, it goes back to the 40s, Tippett-Fisher-Ignenko theorem. So let me do somehow the two easier cases, the Pareto and the Weibull distribution. So if I have that, if I look somehow, this is a cumulative distribution function, and I look somehow at the, I mean, this is somehow the probability that I'm over a threshold x, so the probability that I'm larger than x. So if this tails off like 1 over x to a power plus some kind of slowly varying function, which is a factor of log growth, which only have at most the log, I mean, an oscillation on a logarithmic slow scale. Then if I have this kind of behavior, then the limit, the extreme value law will be a Pareto-Frechet distribution. Instead, if I have my distribution has a maximal value, so I have a maximal value which I cannot overcome, and I look what is somehow the probability to be near to this maximal value, and this goes down polynomially, plus again this kind of log oscillating factors, then I will end up in a Weibull distribution. And so this explains why somehow this is somehow some practical usage, because it's somehow like with the central limit theorem, I have some kind of universal distribution, so I know a priori, I mean, I have somehow a limited range of distribution I have to look at. And so, for example, the easiest things, and this is somehow what people, I mean, people do much more sophisticated thing, but this is somehow widely used, and a lot of you know probably much more about this than I will ever know. But somehow, for the most basic thing which you could do, I mean, you do some kind of log-log plot, and if you want to have if you believe that you're in a Pareto-Frechet kind of thing, then you can read off the parameter just by the inclination of the graph you see, and this is somehow the easiest thing just on a baby form. And so for me, this was somehow, I mean, I just learned this thanks to Valerio, just more or less recently. For me, this was somehow what finally made me understand that actually you can do something reasonable about extremes. I mean, how you can stay statistically about something which you have never seen didn't make any sense to me. I mean, that was somehow just a nonsensical kind of argument in itself, because, I mean, if you think in a Gaussian paradigm, I mean, you will never see what is happening in the tail, so why you should be able to predict anything. And here somehow one sees that somehow if one is somehow in the asymptotic regime, one has a very good and stable kind of prediction power. Now, so this is somehow the IID case is only, let's say, the paradigmatic case, and these things are pretty stable. So, I mean, it's like the central limit theorem. If you are near enough to the IID case, everything will be essentially the same. So, and you have somehow to check in principle two properties. One is somehow this over threshold property, which I described you before, and the other one is you need some kind of mixing property if you don't have independence. No? So you can, it's like always somehow, if things are mixing enough, then somehow things behave more or less like independent. People spend somehow a lot of work, somehow what is a weak condition to do this, and you can then just identify it, and you can also get a distribution for the return of the maxima if somehow you have enough mixing, and then somehow you can go further and try to look somehow if you have for some events which somehow regularly occur, and somehow you can somehow make a lot of theory about it. Now, I'm interested somehow in another case, what happens if somehow, if you're not in a stochastic situation, but the underlying thing is essentially a dynamical system. So I look at a dynamical system, and I mean, the most primitive way to look at the large time behavior is to be interested in the invariant measure. So I assume that somehow we have a invariant measure, and somehow my discussion is on such a superficial level that I don't go, somehow these technical properties will not enter. But I mean, we think conceptually about somehow a nice physical measure, as a B measure, something like this. which somehow, for people who don't know anything about, you can see this somehow as some kind of small noise limit of the system. So if you make a small noise and then you look at somehow at the limit, what you get for the invariant measure. And so somehow this invariant measure is somehow roughly describing you what will happening at large time. Now for extreme values for dynamical systems, there was a huge somehow activity, and I list some name, and I'm sure that I forgot people. Let me just describe, so just see this as some names, but not as a full list. Let me see, if I look, they looked at observables mainly of this kind of type. So you just take a point and you measure the distance of the point and you take some function of this. Okay, let's take a power, to be simple. This doesn't change anything. So, so the theory is very easy if this point is inside of your compact attractor. So you assume the system has an attractor and you assume this x is happily inside, and then somehow you just do as before, you just follow a trajectory and just compute the maxima. So the question is, what is the distribution of this maxima? And because your attractor is compact, you mean you have a threshold, and so somehow what you expect, it has to be widely distributed if you have enough mixing. Okay. So, and I will explain you why this is somehow the case. I'll just give you the basic idea of the proof. So, so assume somehow your system is nice enough, and you have somehow some local splitting of your system, and somehow you have somehow the dimension of the expanding directions, and you assume somehow that the attractor, so you have somehow local splitting, you assume that the situation is somehow very regular, and that in the other direction, the other direction, the attractor, let's say, looks more or less like a counter set. So if you're in a situation like this, so what we should expect to happen, then somehow this over threshold thing is nothing else than the rescaling of the volume. Yeah? It's just a one-to-one reformulation. If you want to compute the over threshold under the invariant measure, it's just somehow nothing else in the volume. So you reduce it to something people consider classically. And so what you really have to look at, you have to look actually at this fraction, and you have to show that this fraction is somehow has somehow the right the logarithm has somehow this right scaling, so it should be somehow equal to some power, and you will see that this somehow, you can just see from this easy consideration what you should expect is that this will behave with this kind of index. And then somehow, if you want to have a proper a proper extreme value law, you have to prove that you have enough mixing properties, and then somehow you can go through this, and this is somehow clearly a non-trivial problem, because you need somehow good knowledge about the underlying dynamical systems to get at this result. So why we were interested somehow, or it's Valerio and this group were interested in to look something different. So because somehow this approach has some restriction from a, let's say, maybe if you want to, from a more practical point of view. So first of all, you have to choose your point inside of the attractor to make this work, because then somehow you have somehow really the scaling like the volume. Then somehow you have to use chaotic system. Typically somehow the most of the examples were done in low dimension, and so what somehow all of this boils down to is that essentially what we use here, that we said we have some geometrical link between the structure of the attractor and the structure of the observable. So this somehow you can only do this, and that's somehow what I mean. You have somehow to, need to know in some sense your system very well, because you somehow cook up your observable in such a way somehow that you can reduce everything to a quantity you know very well. Now, what is somehow, if you do somehow, so if you think about metrological systems, so typically you have a very high dimensional system, the attractor will be complicated, and and I mean, you're not really sure how things look like. But the observable will typically be something, I mean, somehow you will look only at special observables, which are not directly related to the structure of the dynamical system. You will look something, I don't know, like energy, momentum, density, a typical kind of additive kind of function, which you hope somehow that this adding up will improve the regularity of the thing you look at. So you don't observe somehow, I don't know, the temperature in a particular corner or something like this. You make some kind of averages of thing and hope that this will give you some more kind of regularity. So the question was somehow we posed, okay, assume somehow we don't assume any relation between our observable and the dynamical system. So what is somehow the geometrical picture which will appear in this situation? Okay, so if the idea somehow you have to think about is that the attractor is a very thin thing, and so the maximum of this A will be typically not obtained inside of the attractor. So if you now, the maximum of the function will not be attained on the attractor, but the maximum on the attractor, so I mean, if you somehow only look at the values which you take on the attractor, and there somehow, that means somehow that the function AX on this is not in its overall global maximum, so it will have a linear piece. So in principle, it will be a linear function and not a quadratic function. So before we had some kind of quadratic function, so these functions are linear. And for the level we are working at, so in principle, somehow a linear function is enough, so the general function essentially is a linear function. Now, if you want to look how the measure is scaling, so you have to look again at this kind of over threshold. I mean, this is somehow the relative over threshold event, and you will see, you will get somehow the scaling you get. I mean, if you have just the volume scaling plus some factor delta, the power, and then you see that you should somehow, you get a formula like this, and somehow in a long series of, in a paper, they looked at different examples trying to get somehow different scaling results. And I will try to explain you why we expect that something like this is a reasonable conjecture and what are somehow the limitations of this conjecture. Okay, so this is related to a geometrical picture. So if I denote the attractor, let's call it omega, and A is locally finite, and because somehow the linear function has a maximum on the attractor at this point, it means somehow that the situation has to be looking somehow like that. So you have somehow your linear function, so which is decaying in this direction, and then somehow the attractor comes, and because somehow it assumes it is the point of the maximum, so this thing has to look like locally like that. Yeah? So it has to locally look like a parabola. So that means if you want to compute something like this, you have to imagine that this looks like a paraboloid cut by a plane. And so in principle, everything will boil down is somehow how is the geometrical relation between this kind of fundamental directions you have in this point and the plane. Now, the first thing is what you can observe is somehow that the unstable directions have to be normal to this, because somehow in the unstable direction the attractor will be like a smooth thing, and so if you're not normal in this direction, you will not be in a maximum. I mean, this is somehow a elementary kind of observation. And somehow if, and that's not so clear if this is really happening, so if you are not exactly parallel to one of the fundamental directions in the stable direction, then the volume should in the stable direction scale like ds, and because of the parabolic it should scale like the square root in the other one. And then you get this kind of things working. So the question is somehow, this is somehow the big if. Yeah, that's. No, we had this discussion. It's the same. It's the same. It's parallel to one of the stable fundamental. It's one of the directions of the contraction. It's parallel to the manifold. It's parallel to the manifold, but okay. Now, so what are the problems? So the first somehow technical problem we have somehow the hyperbolic theory works for a generic point in the attractor, and we will be somehow on a surface. This thing will be automatically on the surface. The surface is of measure 0 typically. So, and now somehow we have the same discussion before. Is somehow this kind of orientation you have here in some sense generic. And you can very easily, if you make an easy example, if you look at a horseshoe, you can very easily see, yes, it will be true, but if I start now to deform, I make somehow I deform the horseshoe differentially, then it will be actually wrong. Then somehow I will have always this kind of special kind of orientation. Because somehow being on the surface means somehow the inclination of the plane will choose the point where you take the maximum. Yeah? So it will not be a random point on the surface. It will be in some sense a particular point. And so there's somehow some deep relation between how your manifold is embedded and where somehow you touch it. And so what I don't know is somehow I don't know how to compute is somehow what happens somehow if I try to deform these things in a more generic way. Will this property still remain or will it disappear? So what the conclusion is of this is somehow that this kind of result or this kind of conjecture we have is not stable in the usual categories, because I mean these two are both hyperbolic systems. For one it's true, and for the other, I mean XMA system for one, and then it's true, for the other one it's not. Yeah? So it means, because it has something to do how things are embedded. It has not to do with the internal structure. Okay, so let me come to another. Okay, it's a pleasure to introduce this here. So the linear response theory of we try to use the linear response theory to get an idea what happens if we start to perturb the dynamical system. And okay, I will not introduce this in deeper detail. So there's some kind of perturbative expansion which somehow give you some idea how to differentiate actually ergodic means of observables. So everything is, you have to appreciate that everything is very chaotic. Somehow the support of the invariant measure is very singular. So if you move your system, the track and everything will change in a very bad way. But an expression like this behaves very nicely. And so if you do that because you can see that actually the shape parameter, if you just use the formula which we had before, you can actually show that you can relate the shape parameter with moments, and where somehow the moments are the moments of the conditional distribution over threshold. And so this kind of theory start to be applicable, and so you should expect that this shape parameter will be also nicely behaving under perturbation. The problem is in this case again that we have some kind of change of limit. So this we don't know how to prove that, but at least somehow for practical purpose you should expect somehow, if you do it experimentally, I mean just numerically, and you only go to a finite precision, this will be for sure true. And so if you just look that, so you actually what you can see if you believe in the formula which I gave before, then you can see that the response theory will tells you that also from this will follow that the stable dimension will be somehow smoothly behave under this kind of perturbation. So finally, so what is the open problem? So the open problem is somehow we have somehow this one if, and somehow the question is how generically is this, and for me it's also not completely clear what is the best way to trying to answer this kind of question. Okay, we started to do some numerical investigation and where we somehow see sometimes of these problems, and sometimes we can somehow identify why things behave irregularly because we're in a very untypical point. So the other problem maybe that it has something to do with low dimension, and somehow we are just zooming too much into the fine structure. I mean, this is the classical kind of problem somehow. If you ask too much, I mean, you will always somehow be able to construct a counterexample. And we know somehow that in reality people apply this kind of theory. So it must work in some sense. But it may not work if you look at any observable. Maybe you need somehow to use that you somehow have a high dimensional system to have another kind of stabilization. So that's somehow what we need is some kind of universality. If we not have kind of universality, it essentially defy the idea of having extremes. So then it's a question, that's exactly what I described. It's the influence of scale. Can there have something? Or it maybe has something to do with symmetry. Because in a lot of stations I have somehow identical pieces which are interacting, and they're not somehow a randomly cooked up system. Or somehow I have to look at something which tell me in which way I have to deform the system. And maybe somehow what means stable for me means here something different, because this is somehow a thing which doesn't depend on the internal geometry of the attractors, but how the attractor is lying inside of a bigger thing. So, yeah, so that's one reason why I'm here. I hope, for a lively discussion.
So, comments?
Yeah, I have one question about the genericity problem that you asked. There's a Lasota-York picture in which you have partial dimensions which are integers including into the stable regime with just one partial dimension which may be fractions.
Yes.
Do you believe in that? Is there any evidence that this might be true or false?
I don't know. This is a hypothesis by this people, or it's
conjecture. There are counterexamples, but the idea is that it might be generic, and in fact, it has been proved for chaotic.
No, I don't know. I'm not sure anything about that.
Okay.
So in that relation for the exponent that you gave, there was an expression where you related that to moments of the extreme value distribution. Is it clear that these moments exist?
No, it's over threshold, and we're in a compact attractor, so they exist for sure. They're bound.
Okay, it's a compactivity that you mean.
Yeah, so that's no problem.
John?
Just a comment. In many geophysical applications, turbulent applications, you have scalings, you have long-range dependency. So strictly speaking, you're not in kind of a mixing situation. And
Yes.
so anyway, there's some results to do with multifractal phase transitions and this kind of stuff, but they're not, there's not a real theory about it.
Yeah.
But anyway, I'm just wondering if you had any idea if you could extend this in some way, but presumably a kind of a different framework that you need.
I don't know. If you have something like, if you have some dependence for which you know some structure, you may have some chance. So.
Just sort of followed up that comment by saying, well, there's a lot of work going on asymptotic limits of the equations of the atmosphere and ocean. Can those be used to tell you about the structure of the attractor and help sort of study?
I don't know.
Because in principle, you can say that if you say the solution is close to asymptotic limit, you can say in some sense that's an attractor.
Yeah.
I don't know if you make that rigorous, and then obviously in the atmosphere there's a lot of different regimes, so you can't just say there is one attractor, but you start constructing some idea of the attractor.
Yeah.
comment.
Yeah, I mean, but that's somehow, the point is somehow that exactly, I mean, this is somehow, we want somehow to get some relation between the extremes and the attractor. So you can then play in all directions. I mean, you can try somehow to, if you see some of these extremes, you can maybe get some idea of the attractor. If you have some idea of the attractor, you may get some ideas of the extremes and try to conclude something from it.
One second comment on this. I mean, one of the results is that you get that the extremal that the index, that the shape parameters goes with the inverse of the dimension. So if it's something high dimensional, this should go to 0, which is a good sign because it suggests that the Gamble distribution should be the generic model you get in many data, which is, I mean, practically not so false, and somehow related to what Sean was saying. I mean, if you have something which is out of the picture of a dynamical system, so I mean, if you think about precipitation, where you have huge inputs of energy, transformation of energies, these might have different properties that you don't see here.
Yeah, I mean, you ended on questions, but I assume that you have some success in this program. So can you give some simple examples where you have something which is not 1 over the distance to a point?
Yes, I mean, the horseshoe was an example. I mean, that's one of the easy ones.
Even with the Henon, if you do Henon and you take as observable x, so that's the distance, you get that the scaling obeys the numbers you get with good precision. So you get, so if you do the distance, you get as a scaling, you get from the scaling actually very precise estimate of the dimension. So the local dimension 1.26, which is good. If you do the other observable, the x observable, the physical observable, you get 0.76, which is what you should get. So you get the job, at least that picture seems to have merits. But if we are evil with ourselves and we deform it, we could have some problems. But that's exactly what Tobias was mentioning.
How do you have to deform the horseshoe to get a non-generic?
I mean, for the horseshoe, you just curve it. Should be enough, I think. I mean, I think you curve it. I think it should be enough.
But you make the observable hip towards the planar.
No, if you have a planar thing, it works because you have two because somehow this plane is atypical. I mean, if you take a random plane, you will always be in the corner. Yeah. If you have a rectangle, I mean, if you have a square and you try to make a maximum, you will be always somehow more or less in the corner. Only if you're exactly parallel, you will do it. I mean, that's somehow, so you have to have a geometric conspiracy to do that. Yeah. But if you somehow curve these things, then somehow the things are not cyclical.
Other comments or remarks or questions? Okay, if not, thank you again.